chapter a little bit different. But I can tell you it's very, very similar to what you just did. All right. Well, the chapter is on solutions, and Ms. Founds, she was going online, and she found a bunch of stickers. So you want to know if I want to have some? I said, sure, I'll take this one right here. You know that, right? If you're not part of the solution, you're part of the... You ever heard people say that? You're part of the problem? Oh, no. But in chemistry, you say if you're not part of the solution, you're part of the precipitate. But, okay. Ever heard that before? Let me see if I can send on. Here's another one she had. Here. Okay, that's pretty good. Okay, that's pretty good. I like these. This one, if you happen to take second year chemistry, we actually get into a thing called organic chemistry. Organic chemistry is carbon compounds, and caffeine is certainly an organic compound, and there's the structure. Now, you're not taking that class, so I'll show you real quickly what they mean here. See these sticks? At the end of every stick is a carbon atom. And if it's not a carbon atom, I have to let you know. See that guy there? It's not a carbon, it's nitrogen. But guess what's right there? Carbon, carbon, carbon. See that? So at the end of every stick, if I don't tell you, it's carbon. Anyway, so a lot of people see these kind of diagrams, but they don't know what they mean. And, okay, so anyway, there's that one. And, there's some, okay, that's it. So here we are. This chapter here is called Solution Stoichiometry. So we said one more chapter that has stoichiometry, but it's called Solution Stoichiometry. Now, I'll tell you why I think this is important. When you go to a doctor, and there's something wrong with you, say, and they want a sample of your blood, or they want a sample of your urine, or if you're really, something serious is wrong, they might even want a sample of your spinal fluid. That's serious, okay? But what are they looking for? If they take the blood out in a little test tube and they talk to it and say, well, how much iron is in there? It never says anything. Or they look at your urine, how much sugar is in that urine? And it never says anything. So they have to find out, don't they? Matter of fact, I would say the majority of chemistry that takes place on this planet by chemists, it's not because you give them 5.36 grams of, and they have to figure out, very few chemistries like that. Almost all the chemistry is things that are in solutions. So solution chemistry is big. It's really important. Now, we have, I'm going to show you something here. I have some good and bad news for you. This page right here, the good news is that I will teach you about solutions, but the bad news is that when it comes to concentration, you have to be a little bit smarter than the average person, okay? And I'll show you what I'm talking about. Take a look at this right here, and take a look at this right here, and take a look at this right here, okay? Now, which one of these boxes has more dots in it? Which one has more chemicals in it? Everybody, which box? A or B? Which one has more chemicals in it? A. Count them up. There's more chemicals in A than there are in B, right? Now look at C. C has actually less dots than A, but it said it's the most concentrated. What does that mean? Why? Which one of these two is more concentrated? Like, if I could draw these the same size, then this would be more concentrated because it has more chemicals per volume. Now, this is a thing called a ratio. Now, I know you're very smart. You're very smart. but the human mind has a little bit of difficulty with ratios, okay? This is most concentrated because it has the most per volume. It's like the most concentrated. So we're going to use words you've heard of before. Hey, that coffee is too strong. What do you mean by that? It's too what? Hey, this is too watered down. What word do you use to say watered down? Diluted. It's too dilute. We use those words. And then sometimes it happens to be just the right concentration for you, like that. So I need to show you something. Okay. The ratios, the human mind has a little bit of trouble with this, all right? I'll give you an example. Let's say, do you remember studying density in middle school? I think Miss West does that. Did you guys do density? We had in our first semester. Density is what? Mass over what? All right, now let me give an example, okay? Let's say something has a mass of 80 grams and a volume of 100 milliliters. Okay, so what is the density of that material? Sorry, I'm off the screen. What's the density of this material? 80 divided by 100 is 0.8 what? Grams. Okay, so the density of this is less than water. Water is 1, so it's actually less dense than water. Now, you say, well, so what? That's pretty easy. You just plug the numbers in and you divide. And what's so hard about that? Here's what's hard about ratios. What's the density of half of this material? So let's say you have this material and you found the density is 0.8. What's the density of half of it? And I know your mind automatically is going to say 0.4 grams per milliliter. And that's wrong. Your mind, when I say half, you think everything is in half. So here's your problem. If you want half of that material, that means instead of 80 grams, it was what? 40 grams, but instead of 100 milliliters, it was what? So now, what happens when you cut the mass and the volume in half? What happens? What's the density of half of the material? It's the same number. So you don't like that. But that's the way ratios are. You know that? I'll give you one more example, then I'll move on to something else, all right? In math, have you ever found the slope of a line? Have you guys had enough math? You've done slope, haven't you? Okay, ready? All right. Did you ever hear your math teacher say, what is this? How many slopes does a straight line have? Raise your hand if your teacher's ever told you that. Uh-oh. All right. How many slopes does a straight line have? Are you kidding me? Have you done slope? Have you done slope? Oh, okay. So what they did is they showed you how to plug and chug. It means y2 minus y1 over x2 minus x1. And isn't that how you did it? And he said, I'm smart. I know slope. Well, you know how to plug and chug, right? But I'm surprised she hadn't told you this. Slope is steepness, isn't it? Which part of the line is steeper? This or this? Which part of the line is steeper? If you were walking on a hill, and I say, which one's steeper, here or here? What's the answer? Because slope is steepness, right? But here's a slope of like 0.1, a slope of 2, slope of 3, slope of 4. Yes, no? So it's steepness, isn't it? Did they say rise over run? Did your teacher say that? So which one's more steep, here or here? They're the same. And your math teacher should have told you this. The straight line has only one slope. And I want you to ask you this question here. Ready? How in the world, see this x number here and this x number over here? They're not the same. This x number is way bigger than that x number, isn't it? But what about the y number? And what about that y number? Oh man, this x number is 5 times bigger than that one. And this Y number is 5 times bigger than that too. And you know what that means? When you have something where you get twice as big and I get twice as big, or you get 5 times bigger and I get 5 times bigger, you always get a straight line graph, and that's called a direct proportionality. And what that means is, everybody looking? Did X stay the same? No. Did Y stay the same? No. Did anything stay the same during that graph? Yes. What's the one thing that stayed the same? Slope. And slope is a ratio. So let me ask you this question here, okay? You have this coffee, and you said, that coffee is too strong. And then I take half of that cup of coffee, and you taste it again. What are you going to say? All right, it's just perfect now. Is that what you're going to say? No, it's got the same concentration, doesn't it? Then I give you one drop of that coffee, and what are you going to say? Oh, no, it's the same, isn't it? And concentration is a ratio. You have to be ready for that. See that? And so we're going to make solutions, for example. If you make a solution, and you don't know what this is yet, but say it's a 3 molar solution. Okay, that's its concentration. What if I take half of that solution? What's the concentration of half of it? 3 molar. What's the concentration of 1 drop of it? 3 molar. Got it? Do you know that, maybe you don't know this, the density of gold is about, it's close to 20 grams per cubic centimeter. Get that? What's the density of half of that piece of gold? What is it? Isn't it still 20? What if I have a little speck of gold? What's the density of a little speck of gold? 20. What if I have a planet that's solid gold? What's the density of that planet? 20. All right, the only reason I want to caution you this is I don't want you to fall in that trap. Concentration is a ratio, and you can understand it as long as you're ready to say, I get it. There's a little trap with ratios like that. Why does this straight line only have one slope? Because when you make the X 5 times bigger and you make the Y 5 times bigger, something doesn't change. The ratio. Slope is a ratio, isn't it? All right, so guess what? Any amount of that is more concentrated than any amount of that. Give me 1 drop of that and a swimming pool of that. Which one's more concentrated? This one. Now, if I ask you which one has more chemicals in it, the swimming pool. But which one's more concentrated? This. All right, so that's number 1. Number 2, the other bad news. The other bad news is that over time, there have been many ways of expressing concentration. Okay, now I'm going to help you. It's not that bad. Here they are. Hey, how concentrated is that? 5 grams per 100 grams of solvent. It's a 10% by mass solution. It's 3 parts per million. No, it's 1.5 parts per billion. And so, if you look at scientists, some scientists, they want to use this concentration unit. For people who are looking at things that are tiny, tiny amounts of it in the environment, some things like plutonium is like the most poisonous thing on the planet. And they have to have ways of detecting maybe 1 part per trillion. 1 part per trillion is too much plutonium to be in the environment. Get that? I'm even surprised we can measure 1 part in a trillion. We have planes that even fly around the world, and they sample the air, and they're looking for things like 1 part per billion, something like that. All right. Now, I will tell you right here, without a doubt, the one I'm going to spend most of my time on is the one that chemists use the most frequently, and it's a thing called molarity. And molarity has a definition. It says moles of solute over liters of solution. You're going to hear me say that over and over and over, and so we'll be doing that quite a bit. All right. Are you okay so far? All right. Now, what I'm going to show you is this. By the way, I want to make sure you, these two words here. What's the difference between this and this? Solute and solvent. Okay, what's the difference? Matter of fact, I'm trying to think your lab. Is your lab? I think your lab talks about, maybe not. Oh, you mean. What's a solute and what's a solvent? We actually had this in the first semester. You probably don't remember it. What's a solute and what's a solvent? Let's say you had some salt. You put in a gallon of water. You stir it up and you make a solution. A solution is where you make a mixture, right? A solution is a mixture, right? It's not like a new compound. It's a mixture. And so, which one is the solute? Salt or water? Which one is the solute? I need some help here. We're going too slow. The salt. Okay, so the solute is a thing that gets dissolved. And what is the solvent? So if I make a salt water, and what is the solution? It's the mixture of the solute and the solvent, isn't it? And so if I said, everybody, your assignment tonight is to make me some salt water, and you all came back, and I had some way of measuring it, the concentration, they'd all be different, wouldn't they? There's no way you knew what Noah was going to do. You didn't know what Noah was going to do. You didn't know what anybody here was going to do. So that's why solutions can't be called pure substances. Why? Remember first semester? Because you can make them many ways. And you'd have different concentrations, wouldn't you? So when you made the saltwater solution, the salt got dissolved. That's the solute. And what is it that did the dissolving? That was the water. Now, any of you, does anybody here do their own laundry? You should learn that before you get out of high school, okay? When you go to college, you'll be shocked. Well, who's doing my laundry? Well, I think I'll go home every weekend with a whole bunch of dirty laundry. I don't think so. So you got to learn how to do your own laundry. Now, if you do your own laundry, you know that sometimes you'll get something on your clothes that doesn't, you say, if I put that in a laundry, it's not going to come out. And the soap won't be able to dissolve it, will it? And what do you put on there? Have you ever seen any of these things you buy and you squirt it on there, you rub it on there? What you did is you're looking for a different solvent. Have anybody ever used hairspray to get inks out? If you get a little ink on a shirt, your favorite shirt, you know the hairspray, the material in hairspray is not water. And it's a good solvent. And it's a different kind of solvent. Grass stain, anybody know how you get grass stain out? Okay. Anyway, they have products. I tell you what, water is called the universal solvent, not because it can dissolve everything, but it can dissolve a lot. Water is one of the best solvents in the world. I always think about that when I think about God. I think, before I was a believer, I used to think, well, water, and I knew all the different science stuff about water. But man, the more I think about water, I became a believer when I was 31 years old. The more and more I think about it, it's like, wow, this is an unbelievable molecule. It doesn't act like anybody else very much. It's really unique. And guess what? I have a lot of it in me. I have a lot of it on this planet. And I don't really see that much of it anywhere else. Water's ability to dissolve many materials, that's why you are alive. You're alive because water dissolves so many things. And so when I'm looking for chemicals in your body, they're probably already dissolved in water. When they say, how much iron is in your blood? Is it actual pieces of iron? Or is it the iron ions that are dissolved in the water, in the blood? See that? Hey, what's your potassium level? Potassium? You mean that real highly reactive soft metal that, no, I don't have the metal potassium in my blood. But I do have potassium ions in solution. And that's what they test for. I happen to have a medicine that I take. I've been taking it for over 20 years. And one of the drawbacks of the medicine is if you have to make sure it doesn't deplete the amount of potassium in your body. So like when I go to the doctor once a year, they'll check my blood and they'll say, is my potassium level within the range of normal? And if it is, then I just keep with that medicine. You see that? But if they were to notice that my potassium levels were to drop way lower, my body would not work as well without enough potassium. And so I'd have to maybe start taking a potassium supplement to put more potassium in my body. Okay. All right. So what I'm going to do here is I want to show you about one of the concentration units that's used, but I'm not going to emphasize a huge amount because it's only used for one thing. The one I'm going to emphasize for sure, starting tomorrow, is molarity. But you're not ready for that anyway. So I'm going to start with this guy right here. Let's start with number 1. And this is where you're going to do a little homework assignment. And I'm not going to have it due tomorrow. I'll let you have it due on Monday. Plenty of time. If you're busy tonight, you can do it sometime before Monday. And when I used to teach in the public school, I've taught in the public school for 29 years. This is my 17th year teaching here. But they had these things called end-of-course tests. Has anybody been in the public school and had to have end-of-course tests? Okay. Almost every year, if you took you wouldn't have had chemistry, but the chemistry end-of-course test had this graph on it. And this is the classic chemistry graph, okay? They thought if you're a chemistry student, you would understand this graph. And if your teacher spent any time at all with graphing, then you should be able to understand that. And if you can think, and let me show you what this is about here, okay? This is called the solubility curve. Now, solubility means how much solute can dissolve in how much water. And I could see somebody a long, long time ago trying to figure this out. Let's figure that out. How much NaCl can dissolve in this much water? And they tried it, and they stir, yeah, put some more in there. Yeah, put some more in there. Yeah, put some, that's it. You can't put any more salt in there because it won't dissolve. Okay, write that number down. Now, let's try another chemical. And I can see them making this graph. So let's take a look at the graph. Ready? What is it that can affect the solubility of a solute? Well, one of them is temperature. Got that? So what I'm going to do is I'm going to show you how to read this graph. Whenever you read a graph, you always look at what's on the x-axis and what's on the y-axis. So here we go. Temperature. I get it. Kind of cold. Room temperature in Celsius. Everybody know Celsius about, everybody know what room temperature is? 22, 23. Everybody know that? If you go to Europe, how hot's going to be today? 22. Ooh, that's cold. No, it's not cold. Right. Does everybody know what body temperature is? We did that in the first semester. What's body temperature in Celsius? Uh-oh. What's everybody in the world? Everybody in the world knows their body temperature in Celsius except you. Ask anybody else from another country. What's your normal body temperature? 37. 36.5. See that? 37 is like 98.6, right? Did you know what it was in Fahrenheit? No. Okay, 98.6 is what we call normal body temperature. Anyway, so 37 is what everybody else in the world calls it. So I know that this is like pretty hot. That's 98.6, right? So right here is about room temperature. And so here you go, kind of cold water. Oh, really cold. This is like 0. Ooh, that's like ice water, isn't it? Everybody get it? Ice water, still kind of cold. Warmer, about room temperature water. Getting kind of hot. Boiling water. All right, that's easy. Now let's go to the y-axis. This is the only time in chemistry that I actually see this concentration unit used. So I do it first and get that out of the way. You get it? What's it say? Grams of solute per what? Okay, now, this is not the hero of this chapter. It's very minor. but this is the classic graph that they use this for. And here's what they did. I can see them setting it out. Set out 100 milliliters of water. That's 100 grams, by the way. Put 100 grams of water out. Put another 100 grams of water, okay? And then what kind of water is that? Well, there's 0 degree water. There's 10 degree water. There's 20 degree water. It's hotter, hotter, hotter. How much can you dissolve? How much can you dissolve? Okay. Now we know how to read the graph. Ready? Now let me show you how to do this. Let's start and pick a temperature. Let's pick a temperature and let's pick 10. I'm just going to pick 10 at random. I hereby declare I randomly pick 10 degrees. Now pick a chemical. I don't know. I'm going to randomly pick the chemical called sodium nitrate. Now what I'm going to do is, just like Battleship, ready? I go up here until I hit the graph. Ding, 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 ding. And then I go over here and read that number right there. So everybody see what I just did? All right, now what does that mean? At 10 degrees water, you can put 80 grams of, help me out, 80 grams of sodium nitrate in 100 grams of water and it'll dissolve. And that's the maximum, that's the most you can put in there. All right, everybody stay, are you okay on this? Now, watch this. Well, I wanted to only put 70 grams in there. Fine. If you put 70 grams in there, will it dissolve? Yes. Will it have even more room? You could have put more? Yes. Okay, so we have some words. If you put exactly 80 grams in 100 grams of water at this temperature, you have a thing called a saturated solution. Now, I don't know if your English teacher does this now, but when it rains and rains and rains, they might try to use that word with you. What happens when the ground cannot hold any more water and the water starts running off because the ground is so full? What's that word that they use, meaning completely full? Starts with S. Saturated. That's what this is. A saturated solution says, that's it. You can't put any more sodium nitrate in this water and have it dissolve. So it's saturated. What is any number below 80? 79, 16, 32. What if you only put that many in there? What would be a great word for that solution? What would be a great word? It says, you're not saturated. So there's only one way to be saturated. For this guy right here, 80 grams will saturate 100 grams of water, won't it? But what if you only put 70? Well, your unsaturated solution. It's an unsaturated solution. Yes? Okay. Now, let's try something else now. Let's try and move the water. We're going to heat the water up now. We're going to heat the water up to 20 degrees. Now tell me, how many grams of sodium nitrate do you need to saturate it? 100 grams of water. What do you think? What do you think that number is? That's 85, right? Should be like 86 or 87. All right, look where I'm at. Boink. Boink. All right, that's 80. That's 90. That's 85. What do you say, 87? 86? You should be at least one number away from what I get. I'm not the king or anything like that, but on the other hand, you should be getting pretty close to the number I get. All right, so guess what? If you heat that water up to 20 degrees Celsius, now how many grams can you put in there? It used to be 80, now you can put 87. Yes? Now, so at 20 degrees, what is the saturation level? How many grams of sodium nitrate can you put in there to saturate the solution? 87. Now, this is where it gets good. You make a solution at 20 degrees, you put 87 in there, Yeah, it all dissolves, just like the graph told me it would. But then you let the beaker sit over here and you let it cool off. Uh-oh. You're going to let it cool off down to 10 degrees. What's going to happen? Let's see who's really on the ball today. Who wants to take a chance? Nobody else is taking a chance. Who wants to take a chance? What do you think is going to happen? I got this solution that had 87 grams of sodium nitrate in it at 20 degrees. I let it cool down to 10. Take a chance, Ty. You can do it. Take a chance. Would you think that the solution is still saturated? Yes, no? Okay. So nothing going to happen? Anything going to happen? Okay. Anybody else? Take a chance. Really? Sure? I thought you told me at 10 degrees, 100 grams of water cannot hold any more than what? You told me it can only hold 80. You have 87 in there. So what's your problem? What normally happens is that you'll start seeing crystals on the bottom of your beaker. Well, what happened? And how many grams of sodium nitrate will be sitting on the bottom of the beaker? What do you think, Reynolds? How much? 7 grams of sodium nitrate will be on the bottom of the beaker. You know why? Because at 10 degrees, 100 grams of water cannot dissolve 87. It can only dissolve 80. 7 grams will be sitting there. See that? I know you've gone to a restaurant, and sometimes you get like tea, and not from, especially if you go up north. They don't know what sweet tea is, okay? So you go up north, and you'll put sugar in there, and it's already cold because they put ice in it. See that? And you take your spoon, and you stir and stir, and what do you notice? You notice sometimes all the sugar doesn't dissolve? Okay, because at that temperature, that water can only hold so much sugar. Get that? So what it can't hold falls out. When they make things like rock candy, what you do is, and if you, I've had people do this at home. You want to make crystals. You want to make crystals? Here's what you do. You heat up some water and put in a whole bunch of this chemical, and a whole bunch of it will dissolve at that temperature. Then you let it sit and cool off, and you put something like, do you still do this in middle school or elementary, where you made a jar of some chemical and you didn't know what you were doing, you just did what the teacher told you to do, and then you put a pencil and a little string, and maybe you had like a nut or a bolt or I don't know, maybe a paper clip. Has anybody ever done this? You made a solution, it was really hot, and then you put this here, and there's a string here, and you put it in here, and after it cooled off, you came back after a few days, and what was on here? What was on here? Crystals. How many of you made a crystal somewhere in elementary? I thought they still did that. Nobody? You did? Who did that? What teacher?
I did it at home.
Oh, you did at home. Okay. So anyway, when they make things like rock candy, that's what they do. They heat up hot water and put a lot of sugar in there, and then they put it in little individual things, put these sticks in there, and put a little food coloring in there, and all of a sudden the sugar crystallizes on the stick because it's a rough surface, and it can't hold that much sugar, so it has to go somewhere. So it can either fall to the bottom, or it might collect along your stick, and now you have this thing called rock candy. Anyway, that's the way they make crystals. So we know what saturated is. There's only one way to be saturated. There are many, many ways to be unsaturated, aren't there? And I'm going to tell you about something that's really unusual. Here's something that is real unusual. Now, I don't expect you to think that this happens all the time. But if you're really careful, all right, you can make a solution. Everything's clean. All your glassware is clean. And you make a solution with hot water, and you put gobs and gobs and gobs of chemical in there. And then you set it aside and put it in a place that doesn't vibrate. Put it in a place that's very still and calm. And then let it sit there. And what will happen is something like this. At 20 degrees, 87 grams can be held in there, and you let it cool all the way down. Let's pretend you let it cool all the way down to here. See this? then what should happen, and almost happens 99% of the time, 7 grams will fall to the bottom. But if you're really careful and everything's clean and you don't shake it, you'll see it sitting there. And you won't see anything on the bottom. Now, they have a fancy word for that. It's like, no, you're not supposed to hold that. You're not supposed to be able to dissolve that. That's not normal. And what does that mean? You are what? Super saturated. Now, supersaturation is difficult to obtain, but you can do it. Now, here's what happens to that solution that's supersaturated. I've seen, and I'll show you a video, okay? I'll show you a video tomorrow, where you take a supersaturated solution, and you're not supposed to be able to do that. The graph says you can't do that. Well, I'm doing it. And what they do is they'll throw a single crystal. All they wanted is something to start the pattern. You throw a single crystal in there, and all the stuff that should have fallen to the bottom will come out like that. And it's really neat to watch, okay? It's called supersaturation. Anyway, did you do something like that when you made crystals? Did you stick a paper clip, or what did you do? Yeah, something like that. Anyway, so supersaturation is very unusual. If any kind of vibration, I've seen that before, where somebody just takes like a knife and just taps it. They tap the jar, and the vibration, and all the stuff comes out to the bottom. So anyway, let's take a look at your homework. And this homework is going to be not due tomorrow, because I want to look at this one more time, but due on Monday, okay? Let's do the first one together. Oh, I know. Wait, I forgot to tell you something else. Hey, I'm almost done. By the way, this is called grams of solute per 100 grams of water. Let me go back to one more thing here. Let's say at 10 degrees, how much sodium nitrate can be held in 100 grams of water? 80. Okay, I got that. That's the third time you said that. Well, how many, what about in 200 grams of water? Wait, look at me. This is where you're going to mess up. How much can you dissolve in 200 grams of water? Well, this number tells me you can put 80 grams of this in what? 100 grams of water. I can put 80 grams of sodium nitrate in 100 grams of water. And I know your teachers taught this before. You know how to do a proportion? Remember proportions? Watch now. If you can put 80 grams and 100 grams of, whoops, what's the matter with me? Dumb, okay. If you can put 80 grams of sodium nitrate and 100 grams of water, then here's my question. How many grams of sodium nitrate can you put in, let's make up a number, 250 grams of water? Does everybody know how to do a proportion? Remember how to cross multiply? Have you guys been taught that? Okay, so you get 250 times 80 divided by 100, all right? Anyway, that's what you can use this graph for. So if you see a question over here and ask, well, how much can you dissolve in 300 grams of water? See that? Let's do the first one, and this will be the last thing we do, and I'll stop here. Which substance does not appear to increase greatly its solubility as the temperature increased? Let's take a look. Let's see, sodium nitrate went from like 74, whoa, all the way up to 150, whoa. That really increased the solubility, didn't it? That's not the answer. What am I looking for? Which one does not appear to change very much at all, even though you change the temperature? Which one? Which one looks the most flat? Which graph looks the most flat? That's this guy here, right? This is sodium chloride. Sodium chloride's funny because cold water, you can put about 35, and boiling water, you can only put about 40. You only increased by a little bit. So sodium chloride is kind of funny. You can dissolve almost the same amount in cold water as you can hot water. But look at some of these other ones. Wow, look at this guy. 15 grams of cold water, 75 grams in hot water. That's a huge difference. All right, anyway, I want you to work on this, and I won't have you do it till Monday. And if you have any questions, if you want to work a little bit on it tonight, you said, I had some questions on here, just do that. Have I got that? All right, well, thank you very much.